And if a person has to come up with a theory like that, saying light travels in the form of waves when you can't even see light, then he should have some reason for saying that. And the reason was a British scientist called Thomas Young. He was doing an experiment where he had light pass through two slits in a cardboard. You can imagine that. Two parallel slits in a cardboard, right? And light was passing through it. And he let that light fall on a screen up in front. What do you expect to see on that screen? If you have just, actually he did it with sunlight first. Sunlight was passed through two tiny slits close to each other, parallel to each other, and then you set up a screen on this side. What do you expect to see on the screen? Two bright patches of light, correct? Having the same shape as the slits. If the slits are rectangular, then this is going to be rectangular. But that's not what he found. What he found was, he found alternate dark and bright bands. Instead of two bright patches, he saw several small, bright, and then dark, and then again bright and dark, rectangular bands. He could not explain it. He said, what is happening? How can I explain this? That's why this scientist, Christian Huygens, came up with, you know what? I can explain that if you imagine that light travels in the form of waves. And so let's look at how he tried to explain this property called interference. Now, this property of light is called interference. And you know this word before, two waves coming together, they can affect each other, right? That's what you mean by interference. Before we get there, take a look at this. Light, if it's imagined to travel in the form of a wave, that's how it'll go. If you throw a stone, that's how it'll move, right? As it hits water from air. We know that if it is just particles, and if you have a tiny slit, you just expect a few particles to go through, isn't it? Yeah. If it's a tiny slit. But if it's a wave, then you expect something totally different to happen. And this is what really happened. I just drew something here to show that if you have a point source of light right here, a tiny light bulb or something, it produces waves that go in all directions with the same speed. Therefore, if you join all the crests together, you know the crest and the trough, you join all the crests together, you will get a sphere. That's easy, right? And that sphere will be ever expanding. So that ever expanding sphere is called a wave front. It's called a wave front. There are three types of wave fronts. If it's a point source, you get a spherical wave front as shown in the picture. If it's like a fluorescent lamp, is a fluorescent lamp a point source? It's an extended source, isn't it? You will then get a cylindrical wavefront. And both of these at great distances away from the source will both become plane. Whether it's a spherical wavefront or a cylindrical wavefront, it'll turn into a plane wavefront. You know why? Just imagine the sun. From here, you can imagine that the sun is a point source, right? That's correct because it's so far away. When the wave fronts are produced near the sun, it's going to be spherical. But guess what happens by the time it reaches the earth? Is it going to be spherical anymore? It is, but it's just a tiny part of the sphere that reaches the earth. And you can't even make out how much it's curved because, you know what I'm trying to say, so it's plane. So at great distances, any wavefront becomes a plane wavefront. And although I didn't draw it on this, I want to show you, if it's a plane wavefront, the rays of light are parallel to each other. Do you see that? That's why we've been saying that if a source is at infinity, the rays that come and fall on anything is always parallel. So that's the relation between a wavefront and rays. They are always at right angles. Important point. A wavefront is always at right angles to the ray. And now that also makes it clear that if you have a point source and if the wavefront is spherical, well, now we know why we draw the rays that way, because You see, again at right angles. So a wavefront is always at right angles. So those are the three types of wavefronts. One more time. A spherical wavefront is produced by a point source. A cylindrical wavefront is produced by an extended source, which will be a linear source, like a fluorescent lamp. And a plane wavefront, what did I say? Is either of the two if the source is far away. Okay. Then let's really look at interference and see what it is. This whole chapter depends on this math here. And what you see here are the two slits. S1 and S2 are the two slits. They are rectangular slits, but you know that the cardboard is not turned towards you, right? If it was, then you would have seen the rectangular slits, right? Now you see it this way. The cardboard is kept this way. That's why I only see the width of the slits. You notice that the distance between the two slits is really small, okay? But the distance of the slits from the screen is comparatively large. Therefore, what I'm going to do is I'll label this caps D, capital D, to show that the distance is bigger. And I'll change this to small d. So you know, remember in your mind that small d is the small distance between the two slits. Caps D is the bigger distance between the slits and the screen. That's clear. So now, if you look at the central point here, and be watching, don't you think that the distance from S1 to that point is exactly the same as the distance from S2 to that point? Okay? And what do you think about these two sources? Are they producing waves that have the same wavelength? Because actually you have a source kept somewhere behind. And what's actually happening is that source, the waves from the source is being divided into two. So surely all the characteristics of the waves that are coming through S1 and S2 are the same. Such sources are called coherent sources. C-O-H-E-R-E-N-T. So what do you mean by coherent sources? Coherent sources have the same wavelength. They have the same wavelength. They have the same amplitude. And they are in phase with each other. Three properties. They have the same wavelength, the same amplitude, and they are in phase with each other. Such sources are called coherent sources. All right, so going back, if the wavelengths are the same, and this you need to answer, if the wavelengths are the same, let's imagine that, watch this. This is the first crest, the second, the third. I'm drawing waves. You saw that? Let's imagine that the fourth crest from here reaches there, okay, the fourth one. What can you say about what would be the number of the crest that reaches there from S2? 4. So if two crests come together and their amplitudes are the same, then the total amplitude must be 2A. If their individual amplitudes are A, the total amplitude should be 2A, and intensity is proportional to the square of the amplitude. Therefore, the intensity of light at that point would be 4A squared. That shows that you get brightness there. Okay? But let's assume that now you look at the point P. Is there any chance for two crests to reach that point? What would you say? I'm waiting for you. Is there any chance for two crests? I don't want the fourth and the fourth, but isn't there a chance for maybe the fifth one from S1 and the sixth one from S2 to reach that point P? Yes. Is there a chance? Yes. If so, what is the path difference between the two? Isn't it one wavelength, lambda? Come on. If the path difference is lambda, what do you think you will get? Will you get brightness or darkness? It's a crest and a crest, so you will get brightness. Okay, so if you go further up, you take a point further up, again it's possible that a crest from S1 and a crest from S2 can be superimposed there. Maybe now the path difference is 2 times lambda, but you still get what? Brightness. So generally, what's the condition for brightness? The condition for brightness is that the path difference, I'm sure you know what I mean by path difference, should be equal to m times lambda. The path difference, I'm going to write that later on, but I'm just telling you. The path difference is m lambda. What is m? What's the first value of m? What if you're talking about the central point? Correct? So m can take values 0, 1, 2, 3, 4, etc. So just now I gave you the condition for brightness. The path difference is equal to m times lambda. Now look at this geometric, look at this diagram carefully, and can somebody tell me, this is where the thinking process begins. From this diagram, where is the path difference? Which part is the path difference? We're looking at point P. S2P is greater than S1P. If you are not completely asleep, you know that. S2P is greater than S1P, and I'm asking you, what's the difference between S2P and S1P in this diagram? And you should have taken a few seconds to look down here. You would have told me that this is the path difference. Because if you notice, this line is drawn perpendicular to the line S2P. You see? From here and there, the paths to P are equal. Therefore, the path difference is this tiny part. Can I see your hands if you understood? Oh, good. Now, geometrically, can you find that path difference? Yes, we can. Because if this angle is theta, then this angle is also theta from the symmetry of the diagram. I mean, this angle, what's this? That's theta. And this tiny angle here in the small right angle triangle is also theta. Because you can see two right angle triangles. That's the big one, isn't it? And there you have the small one. What's sine theta in this tiny triangle? What is sine theta? Isn't it opposite side by the hypotenuse? Okay. What's sine theta in the big one? I'm trying to get you to answer that before I write it down. In the big one, it's going to be y, because it's along the y-axis, divided by this distance. But considering that theta is really, really, really small, and this is a highly magnified diagram, sine theta and tan theta would be the same when theta is small. Up to about 10 degrees, they're exactly the same. Therefore, I'm going to write sine theta is equal to y by d. I know it's actually tan theta, but I told you when theta is small, sine theta is equal to tan theta. But so now I have two formulas for sine theta. One from the small, that's from the big, isn't it? That's from the big triangle. And the other one is from the small. Okay, I changed this to small d, and I'm labeling this as x. Okay, so isn't sine theta x divided by small d? Remember, call this small d. Okay. So you have the two. Now put them together and make x the subject. And you have a very important equation there. Although I've not underlined it, please, because that equation shows you what the path difference should be. Okay. But I did tell you that the general condition for brightness was, if you have not forgotten, what was the condition for brightness? Path difference should be equal to m times lambda. And m should be 0, 1, 2, 3, and so on. So, and for dark, oh, stop. I stopped right on time. Can somebody tell me the condition for darkness? You mean the path difference must be lambda by 2. Or it could be 3 lambda by 2. Or 5 lambda by 2. Or because you just want a crest and a trough to be superimposed, isn't it? So the general condition for darkness could be written as m plus half lambda. Does that make sense? Because now if you put m is equal to 0, you're going to get half lambda. You put m is equal to 1, you will get 3 by 2 lambda, right? So that's the condition for darkness. But also remember, sometimes, I don't know exactly what your textbook writes, you could also represent this as m minus half lambda. Does make a difference. Correct? So the condition for darkness could be m minus half lambda. I'm just thinking about the concept questions in exam 4 and the final exam 2 when I'm saying all this. Okay, so can I put these two equations together now? Assuming that P is a point of brightness, can I put these two together? Yes, so that's what I'm going to do. Assuming that P is a point where you get a bright band, put both of those together, and just a simple math. Make X the subject. Make Y the subject, make Y the subject. That's what you get because we substituted for X, right? This is correct? Come on. Now what I want you to do is, before I show it to you, I want you to tell me, you may be possibly thinking already, what's the use of studying all this? Does anybody know the wavelength of light? I did tell you that we can only see the visible region, of course, and which one has the smallest wavelength? I also told you why red is used to signal danger, thinking that that would remind you. I told you that red is used to signal danger because it has the biggest wavelength. So while it has the smallest, which is 400 nanometer, 400 times 10 to the negative 9, just think about what you're saying. How did they get to find out the wavelength that is so small? Do you have a measuring instrument in the lab that can measure so small? Yesterday we used calipers, right? The smallest that it can measure is 1/10th of a millimeter. Calipers, which is small enough, 1/10th of a millimeter. But I'm sure you've heard about a micrometer, have you? Which can measure 1/100th of a millimeter. But if you use light as a measuring tool, you're going to be able to measure to a nanometer. Have you guys heard about thin films? There's a lot of research going on about thin films. Not heard about it. Thin films are so thin that there is no mechanical tool that you can use to find its thickness. You have to use light. What I'm trying to say is, this part is very important because this is how we find the wavelength of each color. You find exactly the wavelength of every color there is. And light, if you use it as a measuring tool, again, it's going to be such an accurate way to measure it. That's how, surely in engineering, you're going to use light to measure. In industry, they use it all the time. You want to measure something accurately to the nanometer, the only way is light. And you have instruments for that. That's why we're doing all this. It's not just for a grade. Keep that in mind. Okay. So now what I want you to do is, how do you find the wavelength? All right, from this equation, give me a method to find the wavelength of light. Look at it carefully. What are the measurable distances? Can you measure this? Oh, definitely. Can you measure the distance between the two slits? Yeah, but you may be thinking, what do you think that distance is? You may be thinking in terms of a millimeter, right? At least. Sometimes it's much smaller than that. Because you know why? The smaller you make D, the bigger the Y. Come on. Didn't I already tell you the value of lambda? Put that in place. Let's imagine this is 1 meter, this is M is 1, this is 1, this is like 400 times 10 to the 9. Are you with me? And you know by now that if this is not really, really small, you won't even know where Y is. Actually, to see interference bands, you need to look at it through a lens. Otherwise, you can't see it. It's not like bright, dark, bright. No, not that big. You need to look at it through a lens. They're so small. Can you find the bandwidth? What do I mean by bandwidth? The width of a band. Because what you're going to see is bright, and then dark, again bright, and then dark. You understood that, right? So give me from this, somebody tell me how to find the width of one band, which I'm going to call B. Get me an expression for B, please. Go ahead. I'll give you 2 minutes. Then you will be able to see. This is the center of a bright band, if you can make out. Well, they have not, this diagram is not exact because they're trying to show that they have unequal widths. You know what I mean? Because according to this diagram, the dark band is small, the bright band is bigger. You see? Okay, but if you imagine that they had the same, isn't this the center of One of the bright bands. And isn't this the center of the next one? So all you got to do is put M is equal to 1 and then put M is equal to 2. And take the difference. Or put M as M and put the next one as M plus 1. Okay. Some of you have to see it to understand. So Y1 is M lambda d by d. Y2 is either plus 1 or minus 1 lambda d by d. Now subtract that. You will get the bandwidth. So what's bandwidth now? Y2 minus Y1, isn't it? So what do you get? If you subtract those two, what do you get? Okay, that's a problem now. Is that a problem now to subtract the right hand sides of these two? This minus this. Honestly? 2m. M
plus 1
lambda d. Thank you so much. That's it. Figure out how when you have the time. I mean, distribute that. You have two terms here, don't you? Minus this, the first term gets cancelled out. And you have what remains, lambda d by d. So that's the formula for bandwidth. And why am I saying that red bands are larger than violet bands? Because it depends on the wavelength. So what happens if you use white light? In all this, when I tried to derive all this, I was assuming that we were using monochromatic light. So what is that? Single wavelength. Because you only saw lambda. But what happens if you had a source which produces white light? Then you have all the wavelengths, isn't it? And so what do you expect to get on the screen? What can you say about the central band? What can you say about the central band? Oh, this chapter and the next are not like the previous two chapters, please remember. The previous two were like, I got the formula here. No, it's getting tougher. No. Okay, what did I ask?
What do you get in the center?
Huh?
What do you get in the center if you use white?
Okay, if you use the white source, what can you say about the center of the screen? What color will it be? If you say white, you have to explain why. What's the value of M for the central one? 0. So does it matter what lambda is? If you multiply anything with 0, you're going to get. So all of them will produce brightness at the center. All the colors come together, so it'll look white. But that's the last white that you will see. The next one, will it be violet or red? The first one that you get. I'm seeing whether you can think. Go back to the formula. My goodness. Go back to the formula. Y depends on what? Lambda. Which one has a smaller lambda? Therefore, you will get that closer to the center. Is it clear enough? And then as you go, you will get the red. That will be for M is equal to, let's say, 1. Wouldn't that repeat again when M is equal to 2? So you will get violet to red, and again violet to red. Are you with me? So now you have different orders of the spectrum. This is called a spectrum, and you have different orders. So M is what shows the order of the spectrum. If M is equal to 1, it's called a first order spectrum. M is equal to 2, it's a second order spectrum. Is it possible that they could overlap? Sometimes, yes. You know what I mean? They need not be exactly like that. First order ends here, the second order begins. No. Sometimes they might overlap. The red of one of them might overlap with the violet of the next one. That's possible, and you can have problems with that. Okay. Chapter interesting, more than what it is already. If you have looked at soap films, soap bubbles in sunlight, you know they look really colorful. But you've never been able to explain why they look colorful. We're going to do it now. Isn't that a thin film? Because outside you have air, inside you have air, and between the two you have a tiny, tiny film of soap. Or even if you look at, you may have seen this, some oil lying on the road sometimes and the sun shines into it. You look at it, it's brilliantly colored. Have you seen it? because oil spreads on the surface, so it's a thin film. And one that you may not have ever seen, which you need to explain to me, if you take an iron rod and just heat it to a very high temperature, you will see colors dancing around its edges. You may have seen this. You heat any metal, normally iron, to a very high temperature, you will see colors. If you watch carefully around it, you will see brilliant colors. What's the thin film there? Because whenever you see colors like that, you must have some thin film. What's the film there? Heat is not a film. It's iron combining with oxygen to give ferric oxide at that very high temperature. If you just have a piece of iron hanging here, it doesn't combine with oxygen. But when you heat it, yes, combines, and you get a thin film. So whenever you have thin films, why do we have colors? Let's look at it. That's the next idea. And we need to explain why we see colors. And if you manage to do that, you would have paid attention. Draw later on. Okay. What you see is two glass plates kept so close to each other with a thin film of air between them. That's very clear, right? So you kept them very close to each other. Like the slide plates, two slides very close to each other, and there's a thin film of air. And you have to assume, because at your level, we need not go deep into details, you're assuming that you're looking at it from straight above. Because you look at the position of the eye, isn't that almost above? Because you could have looked at it from here, couldn't you? Yeah, you could have looked at it from here. Yeah, you could, but you do not need to know the theory for that. Although I will try to tell you after I do this. So the first assumption is you're looking at it from above. Now what are the rays reaching your eye? All right, that's an incident ray. When it hits this glass plate, the top one part of it is reflected, the other part of it is refracted. The refracted part is again reflected from the second glass plate. And surely there should be a small refraction here. If you watch closely, you can see it's bending again, isn't it? So the two rays reach your eye. Let me ask you, I don't think I labeled them 1 and 2. But if I do, which one, if I call this, okay, where am I writing? If I call them 1 and 2, which one of this is traveling through a greater path before it reaches your eye?
2.
All right, 2. Very good. You're so good. If the thickness of the film is T, what's the approximate path difference between the two? See, some give the answer quickly. Some don't even know what I'm talking about. What is the approximate path difference between the two? Which one traveled a greater path? You said 2, right? You're correct. How much greater path did it travel? It went down about T, again T. So the path difference is what? It's not exactly 2T, because if you were to draw a line from here perpendicular to 1, you would have a tiny space here. If you're watching, did you see that? So that's all the theory that there is, but you don't need to know that. So what's the path? Approximately what? The path difference is 2 times the thickness of the film. Agreed? Okay, let me change this a little bit. What if I fill this with a liquid instead of air? I fill it, the setup is the same, except that I fill it with some liquid that has a refractive index n. What would the path difference be now? Geometrically, it would still be 2t, but traveling in a liquid, you have to give it more credit than traveling in air, if you know what I'm trying to say. So now you'll have to say that the path difference is 2t times the refractive index. That's common sense. So the path difference generally is 2nt, where n is the refractive index. So remember this. Traveling 10 centimeters in glass is equal to how many centimeters in air? Oh, maybe I'm too fast. Traveling 10 centimeters in glass is equal to how many centimeters in air? 15 centimeters. Where did she get that? She's from genius, that's why. which you are. But she knows that the refractive index of glass is 1.5. And therefore 10 centimeters in glass is 15 in air. Did everybody get that? You got to keep all this in mind. So what's the path difference? 2nt. That's what is going to come up. Because of all the explanations that I gave you, path difference is approximately 2nt. Okay. But this is the part that sometimes confuses people. Look at this. Is this reflection at this point the same as reflection at the point at this point, at the top and the bottom? Are the reflections the same? Technically, I want to see how closely you watch this diagram. Are the reflections at A and B exactly the same from the physics perspective? Let's see who is very careful. Now look at where they're trying to go when they get reflected. Okay, let's try. Watch this. This ray is trying to go from a less dense. You have to imagine that this is filled with the liquid. Okay, it's not air anymore. Are you listening? It's not air anymore. Okay, so it's trying to go from air into the liquid. So it's trying to go from less dense to more dense, correct? But here, it's trying to go from more dense to less dense. So there's going to be a difference. The difference is that when it tries to go from less dense to more dense, it jumps by a path of lambda by 2. The crest becomes a trough. That makes sense? So whatever hits here, if it is a crest, it's not going to come back as a crest. It's going to come back as the next trough. What's the distance between a crest and the adjacent trough? Lambda by 2. Therefore, there is an additional path. So the path in the material, this is what I told you. The path in the material is always n times the geometrical path difference. Okay, path in air. Oh, I've written 2 now. Okay. Ray 1. Now I've written 1 and 2 twice. Okay, ray 1 is reflection at a denser material, isn't it? Therefore, there is an additional path of lambda by 2. Therefore, the actual path difference, and here, somebody correct me, I think first when I wrote it, I made a mistake. What's the actual path difference between 1 and 2? Which one jumped? Is it 1 or 2 which jumped by lambda by 2? Which one jumped? Which one did jump? 1 or 2? 1. And we know that the 2 was traveling the greater path, isn't it? So would you have to subtract the path difference, or would you have to add to the path difference? I heard both. It's the quality of listening. 2 was traveling more than 1, for sure, we know that. And we would say the path was 2nt. But now we said, no, 1 jumps ahead by what? Lambda by 2. So if 1 jumps ahead, isn't he catching up with 2? So what happened to the path difference? Did it increase or decrease? Decrease. Thank you. So I had to write 2nt minus. So please change it to 2nt minus lambda by 2, which I do at the end, okay, when I realized. So it's 2nt minus lambda by 2, and the condition for brightness, now you see it. The condition for brightness becomes 2nt minus lambda by 2 is m. Isn't this the condition for brightness? Wait a second. The path difference should be equal to m lambda. That's the condition for brightness, correct? But see what happened. What happened? When you take this to the other side, it became plus lambda by 2, and this became the condition for. So now let me ask you the final time. When you talk about thin films and exactly this setup, is this the condition for brightness or is this the condition for darkness? My final question on this part. Is this the condition for brightness? Because if you do not know that, you will not do problems. Okay, I'm asking you, is this the condition for brightness or the condition for darkness in this case? How many people say brightness? Let me see your hands. Thank you. It's the condition for brightness. Because what did we start with? the actual difference for bright, whatever we got, is m lambda, isn't it? This is where some students get confused because they did not listen to me carefully. They're like, didn't you say that was the condition for darkness? Well, you had to listen to me. Because it's going to change again. You're going to see. Can you now think about this? You have air, you have a tiny film of oil, and then you have water. So now you have three materials, right? You have air, oil, and water. And usually the refractive index of oil is less than that of water. Okay? So draw that diagram, please. Just draw one material over another. Call their refractive indices N1, N2, and N3, just like this. Just 1, 2, 3. Make them bigger, smaller, it doesn't matter. That's N1, that's N2, that's N3. Draw an incident ray coming down. Continue. And you're looking at it from here. Beautiful eyes. Okay. Look at it and draw the diagram and give me the condition for path difference, and I'll give you 2 minutes. This is the setup that I tried to give you. Watch this carefully, and in 1 minute I'll be done. N1, N2, N3, I added on to that. This reflection, when is it taking place? Is it trying to go from less dense to more dense? Yes. So wouldn't there be an additional path of lambda by 2 here? Yes. What about this? Is it trying to go from less dense to more dense here again? Because remember, this is oil and this is water. Come on. Yes. So wouldn't there also be an additional path here? Yes. So what's the path difference? We know if you don't consider all this, the path difference is 2nt, correct? Both of them jumped by lambda by 2. It's like two people running in a race. Both jumped by lambda by 2. Did the path difference between them change? See, some are not able to. Both jumped by, let's say, 1 meter. So did the path difference between them change? No. In that condition, no. Are you getting it? Good. But what if, I'm trying to show you the different type of problems that you can have. What if N3 had a smaller refractive index than this, than N2? Then what happens? Then because I can't remember what I wrote, which condition I wrote, okay? So I'm going through each one. Now, that means only this one had an additional path of lambda by 2, so the path difference would be 2nt minus lambda by 2, correct? Or the last case. I know, I've lost some of you, I know. The last case is, what if N3 is less dense? Oh, that's what we talked about now, right? What's the other case that you can think about? What if the additional path is here? When would you have the additional path here? If N2 is less dense than N1, anybody listening to me? N2 is less dense than N1, but N3 is more dense than N2. Got it? So then where is the additional path? Is it here at A or B? At B. Now what's the path difference? Would you add on? The one who was ahead now got an additional jump ahead. So what happened to the path difference? It increased. So what's the path difference now? 2nt plus lambda by 2. I hope you understood all the situations. You should be able to read the problem, draw a diagram, and look at each one carefully. That's why I like this part, because no student can cram now. Because you got to go to that situation, look at it, all right, and remember, if it's reflected, when it's trying to go from less dense to more dense, that's when you have an additional path of lambda by 2. If it's opposite, nothing happens. Keep that in mind. Now, what condition did I write it for? Let's see. What condition? I'll bring it up. I said both at A and B, reflection at more dense medium. So I was talking about air, oil, and water. Let me see your hands if you understood that. Thanks. You are good. Don't have the, what's that? Oil film. But now the problem is, if you look at one point, let's say there's a thin film of oil there, the sun is shining into it, and you just look at one point and start walking away or towards. What's this? Because I don't have space to walk there. So the oil film is there now. I'm looking at just one point and I'm moving away. Just looking at that point. Will the color at that point appear to change or will it be the same? Now, if so, you have to explain why. Wait. Because according to the formula that we have so far, I'm trying to get my students to be really where you can think. When I look at one point and walk away, what really is changing? Is the thickness of the film changing? No. Is the wavelength falling on it changing? No. What is really changing is the rays that get into my eyes are undergoing different refractions. So the angle of refraction is changing. Did you understand? Therefore, in the actual formula, which I tried to give you just one time, this is the actual formula for path difference. And again, I'm saying you need not cram it, but do you notice that in the actual formula you also have what? Cos R. Okay, wait. When you look at it from top, from above, from right above, which is what we did, right? What's the angle of refraction? Remember, you take the angle with the perpendicular, please. So what's the angle of refraction? 0. What's cos 0? 1. Thank you. That's why we didn't have that term. So generally, when you look at one point and start walking away, this is changing. Therefore, different wavelengths satisfy the condition for brightness at the same point, and you will see all those colors at one point. That's what I wrote. White light is a combination of wavelengths, and different angles of refraction gives rise to color combinations that are so beautiful to watch. So today I explain why thin films appear brilliantly colored. There you go. There you go. In college, it was such a pain to set this up. Can you believe that this is called Newton's rings? It's Isaac Newton who first did this. What type of lens do you see? What type of lens is this?
Okay,
Plano convex. And that's a flat glass plate. Okay? And don't you see a thin film between them? A thin film of air? But this film is different from the other films that we've seen before in the sense that in the other cases the thickness was the same throughout. But now, what's the thickness of the air film at this point? 0. And then as you go outwards, what's happening to the thickness? It is increasing gradually. Therefore, what you see will not be rectangular bands. What you see will be circular. I just wanted you to see that. Do you see that? It's a beautiful setup. You will see completely perfect circles, and I hope you understood why they are circular, because the thickness is increasing outwards. And you can even use this. You can fill the space with a liquid, like take that glass plate, put a drop of water on it, and then place the lens. Now, instead of the air film, you have the liquid film, right? And you can use this experiment to find the refractive index of the liquid. In industry, this is the biggest method to find the refractive indices of any unknown liquid. Do you know that they have to test for different substances and make sure that this substance is pure? You know what I mean? This is one of the ways they do it. Take the glass plate. That's why I said using light as a tool, you get accurate results. Aren't we using light now? Light will never speak lies because it's such an accurate measuring tool. It'll give you the refractive index to the millionth point and show you, is this impure or is it pure? That's why I wanted you to see this, nothing else, okay? All right, but I also wrote this. Look at the reflections here. I know you've been troubled. What about reflection at B? What's it trying to do? Come on. Less dense to more dense or more dense to less dense? Oh, you have air here. Okay, more dense to? Okay. What about reflection at C? It's trying to go from air into glass. It's less dense to? Therefore, now the path difference increases, isn't it? That's why it should be 2nt plus lambda by 2. I think I spent a lot of time here, and I've written that here too. I hope everybody is now very clear about what I've been trying to say. Thank you so much. It's exactly 45 minutes. Yeah, I hope this serves you good. Good luck.